Hello, I'm Anna Mackay and this video is on the central limit theorem. So looking at our visual here about rolling different numbers of dice. If we start with one die, you might not be able to see the numbers here very well, but here is a graph to represent the different outcomes we could get. So 1, 2, 3, 4, 5 and 6. They're the different outcomes we could get. Now having a look at what are the probability of each of those happening, it should be uniform, it should be the same. So that if you graph that over time, you would expect to be about a sixth each time. Now if you rolled that many times, it might not quite be that, but they'd be pretty close. But what about rolling 2 dice? So that's rolling 2 and taking the average number that you get. This is what would happen. So with here being 3 and 4 and our average being about 3.5. Just backtracking a step, what would be the average, our expected outcome from rolling 1 die? Our average? Well, again, that would be 3.5 as well. I know you could never roll 3.5, that number doesn't exist, but that's not the point. That's our average of the rolls. So as we go on and increase the number of dice that we roll and find the average, the numbers are still the same, and our mean looks to still be about the same at about that 3.5. And that's because it is. And what else do you notice about this? That it's developing more of a bell shape and more symmetrical. So even though it wasn't to start with. And it's also less spread out. So therefore the chances of rolling here 10 6s is very rare, and therefore the average would be 6. Whereas the chances of rolling 10 numbers and the average being 3.5 or between 3 and 4 is highly likely. So summarising that, as the sample size n increases, so the number of dice roll in this case, the histogram takes on a symmetric bell-shaped distribution and the random variable x bar n is approximately normal. So x bar n is x bar means the average of something, and n is the sample size. So if n was 10, rolling 10 dice and taking the average of those 10, that would be x bar 10. So in more official terminology, the central limit theorem officially says, suppose x is a random variable which is not normally distributed. So x bar is the outcome that, x is the outcome you get from rolling a die in this case, and that wasn't normally distributed. It has a mean of mu, 3.5, and a standard deviation. Now for sufficiently large n, so that's the number of dice that you would be rolling, the distribution of all of those averages, x bar n, is approximately normal, with mean of mu, so the same mu there, and standard deviation, which is smaller, less spread out. So the original sigma divided by the square root of the sample size. And the larger the value of n, the better the approximation will be. So summarising this central limit theorem here, this is the real key point to write down for this, is that the mean of the sample means is approximately equal to the mean of where we started. We sometimes call that the population mean. And in terms of the standard deviation, that the standard deviation of the sample mean, so all of those averages, is approximately equal to the standard deviation of x divided by the square root of the sample size. So in this graph here, we can see that the standard deviation is being divided by a number each time, so that makes it smaller each time. Therefore, the bell curve is getting more narrow, but taller and skinnier, but still centered around the same mean here. Okay, just to hone in on the idea that if the original is not normally distributed, the sample means will be. Now, this is not a graph of the dice, but if our original x was, say, positively skewed, as we take samples from within that, the distribution of the sample means will become normally distributed. And that's the central limit theorem, that's part of it. A few notes here. As a rule of thumb, a lot of textbooks suggest that a sample size of 30 or more is large enough. and that depends on the normality of x. So if x is normally distributed to start with, so for example the heights of teenage boys, because of the enormity of that, you would have a normal distribution to start with. And therefore, whatever samples that you take within that, whatever size they will be normally distributed, because you're taking a selection of, say, 50 boys within that, and it's normally distributed to start with. However, if it, like the dice, wasn't normally distributed to start with, then you would need sample sizes of at least 30 to suggest that the distribution of those averages would be a normal distribution. And that the results regarding the normality of the sample means also apply to the sum. I'll just come on to that in the next slide. So summarizing what we've talked about here, suppose a random variable x has mean of mu and standard deviation of sigma. So imagine the rolling the dice, mean and sigma. Now this sum is what you get from adding up all the numbers, whereas the x bar n is the average. So can you see how they connect? That is the top line of that equation. So you add up all the numbers and divide by how many are there. We learnt that from previous videos that had a mean of n mu and standard deviation this. Well, if you see how these are connected, if you divide that by n, as is being done there, divide by how many are there, that cancels out the n. And if you divide this standard deviation by n, rearrange your square roots, you'd end up with that. So that's how they connect. And summarizing, if x is normally distributed, so the original one that you start with, the population, the distribution of the sample means will also be normally distributed. And if the original one is not, then provided that you're taking samples, preferably 30 or more, then the distribution of those sample means will be normally distributed. So let's get on to an example to put this all into practice. So the volume of soft drink cans is distributed as nearly normal, and we're calling that x, with a mean and standard deviation of these. Now determine the approximate probability that an individual can contains less than 378 mils. So we need a probability statement that a randomly chosen can is less than 378 mils. Now, just to note on why is it not equal to? In continuous numerical data, you can never get an exact value. Imagine 378 mils. Well, how are you measuring that? How many decimal places are you going to? And for every decimal place that you could go to in your measuring system, measuring those milliliters, you could go one more. So there is no such thing as an exact value. So it really doesn't matter if you have it equal to or not. That's the number that's going to be your end point. In this case, your upper end point. So what we will need in our calculators is a lower and upper, a standard deviation and a mean. Our lower is at the lower end, negative E98. Our upper is 378. Now this time around it's just that an individual can. So therefore we use the numbers that we've got up here. Standard deviation of 3 and a mean of 380. And I'll work that out for you. It's 0.252. So that's what you've been doing up to now. This is the new part. What if we want the average volume of a six-pack to be less than 378 mils? What's the chance of that happening? So we know it for an individual can. You can imagine you've got your mean at 378. What's the chances of being 378 or less? I hope I'm doing that the right way around. But what about a six-pack? So the average volume, that means of all 6 cans in that pack, on average are less than 378. So your mean's still 380. What's the chances of it being less than that? All 6 of them. So how do we work that out? Well, first of all, it's usually very handy to write out what is your mean in this case. Well, we know that the means are approximately the same according to the central limit theorem, and the standard deviation is the standard deviation divided by the square root of n. In this case, it's 6. And that is approximately equal to 1.22, so smaller. So our probability statement is actually very similar. But instead of x this time, it's x bar 6. What's the chance of the average of them all being less than 378? So in our calculators, you still need a lower, upper, a standard deviation, and a mean. The lower and the upper are the same. Now, standard deviation. This time around, you put this number because we're dealing with a smaller standard deviation. You can put the exact value there with the surd into your calculator. It's preferable to do that. The mean will be the same according to the central limit theorem. And calculate that and you get 0.051. So a much smaller chance of that happening, that all 6 cans would be less than that. And that probably seems to make sense intuitively. Nearly done. What about the total volume of 24 cans in a carton being greater than 9.1 litres? Now, this time around our sample size is 24, but we're talking about 9.1 litres here. There's a couple ways of doing these types of questions. I like to convert that back into the stuff that we've been talking about. So we've been in millilitres up to now. So what I mean by that is my probability statement is going to be, what's the chance that the average of those 24 cans is greater than, now that many mils, 9,100, but I'm going to divide that by 24. So my probability statement is now going to be, what's the chance that the average of all of 24 cans is greater than 379.17 mils? That's something easier to get our head around. So what would our mean be for 24 cans? Well, according to the central limit theorem, it's actually the same as it was for x, which means it's still about 380. So we're thinking, okay, what are the chances of the average of all of the cans being more than this? But our standard deviation is going to be smaller. And the way we work that out for x bar 24 is the original standard deviation divided by the square root of 24, and it's 0.612. So when we come to work out this in our calculator, the probability statement, you still need to write the lower, the upper, the standard deviation, and the mean. Because when you get marked in tests and exams, these questions have the standard deviation change each time, depending on the sample size. And you must articulate what standard deviation you are using in that question. And if you don't, and you get the wrong answer, you can't get any marks found for you. All right, and that comes out to be that. So a high chance of that happening. And to finish off, can we say that x bar 6 is normally distributed? Explain your answer. So your brain should go, 6, well that's a small number. So initially you might say that 6 may not be a large enough sample. A large enough sample. What number did the central limit theorem prefer us to have? 30. However, what about x? Is it normally distributed or not? Now, if you go back and read the original question, so we say it should be normally distributed. So this is the way you answer these types of questions. It should be normally distributed as x is nearly normal. So that was stated at the beginning of the question, and so we can state that fact here. So that's the end of this video. If you liked it, give it a thumbs up. And the next video is called Confidence Intervals Part 1 of 2, where I take you through how confidence intervals come to be. Thank you.